Planetarium is the Focault pendulum, and so now I will punish you with that. And this is a two-way presentation, so ask questions. It'll be fun. Okay, we have the pendulum. You've probably seen it. Some basics about it. It was made in 1967 by Academy Pendulum. They are still in business. You can still buy a pendulum from them. Cable's about 35 feet long. The bob at the bottom is 235 pounds. It takes 6 seconds for that bob to swing out and back. We'll call that the pendulum period. And since ancient times, people have noticed that a pendulum in the northern hemisphere has a tendency to turn clockwise. But for the longest time, nobody really understood why. They thought it was a defect or they didn't really know. And then in 1851, this French mathematician, Focault, said, hey guys, it's because the Earth is rotating. And everyone was like, oh duh, why didn't you figure that out? It makes perfect sense. And so at our latitude, the pendulum should do a complete rotation in 37 hours. Now, Ian has volunteered to be the Earth. The easiest way to vision, go ahead and start rotating. Which way do you want it this way? So if I was to start a pendulum swinging at the North Pole.
Is this real time spinning?
Yeah. Slowly down.
Terror-free.
So if we started a pendulum swinging above the North Pole, it wouldn't even really know if the Earth was turning or not. Because from my perspective out in space, it's just going to swing left, right, forever. But what if you were standing on Ian's head? What would it look like the pendulum was doing?
Rotating.
Yeah, it would appear to you that the pendulum is turning, does a complete rotation once a day. Now there's an interesting behavior, so we get a rotation once a day here. As we move the pendulum off of the North Pole towards the equator, its rotation slows down, and then it actually stops at the equator. So if we were to start a pendulum swinging in any direction at the equator, let's say north-south, and I started swinging here, it just continues to swing north-south all the way around, and it has no tendency to rotate. If we start to move the pendulum south of the equator, now it starts to turn counterclockwise, and then when we get to the South Pole, it's going to do one rotation per day counterclockwise. And that's what Focault taught us in 1851. So that's kind of super fun. Thank you, Ian. Now, our pendulum, with its geometry, happens to swing out and back in about 6.6 seconds.
Is there some mechanism that keeps it at 6.6 seconds?
No, we're going to talk about that right now. If we wanted to swing faster, let's say 5 seconds or something, how could we do that? What if we added some weight to it? Would that speed it up or slow it down, or is that
Slow it down.
Slow it down.
Slow it down? Who said slow down? We got 2, 3, 4, 5 slow downs. Who said we add weight to it, swing faster? Any swing fasters? No swing fasters? Any trick questions? Anybody think that's a trick question? Trick question! Yes, let me ask you what at first doesn't seem like an equivalent question, but actually is.
Oh.
What falls faster? A cannonball or a softball? Same! Well, all we've done with the pendulum is we just tied a string to it. It's the same weight falling through a gravitational field. Yep. So yeah, if we added weight to it, added mass to it, it wouldn't affect the period. What if we, instead of having it swing like this, we gave it a little bit bigger swing? Would that speed it up?
No.
Slow it down slightly.
Would it slow it down? Yeah. Actually, basically it doesn't affect the period either. And this is fascinatingly, this is Galileo in the late 1500s was so bored at church listening to God talk. And he started watching the lanterns, and he noticed that a lantern with a small swing had the same period it had the same period when it had a bigger swing. And they didn't have a stopwatch back then, so he actually was using his pulse as a stopwatch. I mean, this is how exciting God talking. And so he figured that out, that the period of a pendulum is independent of the amplitude of its swing. Okay, what if we change the length of the cable? Would that change the period of the pendulum? Yes, quite dramatically. If it was 1 inch long, it would be swinging like this. And there are actually pendulums in Europe. So our pendulum's like 10 meters, 10, 11 meters. There are pendulums in Europe that are like 40 meters tall. And they take like 14 seconds for the bobs to swing all the way out and all the way back. They're really, really slow because they're really, really long. So that's the easy thing we can change to make the pendulum swing faster. The other thing that we would have a harder time changing, but at least conceptually we could do, is we could change the strength of gravity. Like if we took it to the surface of a neutron star, it would be swinging crazy fast like this, or if we took it to the moon, it would be just barely, it would slow way down. So you can change length of the gravity and change the period of the pendulum.
What about altitude on Earth?
That would change gravity slightly, so that would have a very small impact to gravity. Somebody else?
Just wanted to point out that if you took it to the surface of a neutron star, it's more likely that the cable would snap.
Yeah, this is a thought experiment.
What about if you're right next to a massive big mountain?
Yep, that could change some gravitational influences for sure. It would probably be too small to detect because gravity is a very weak force.
It would just change the direction of the gravitational field, but it would still swing with perpendicular to that.
That's probably true. That sounds correct.
That's what you want to hear.
Bill?
Is there subjected to a little bit of friction, like air friction?
Yes, let's talk about that.
And
Now, the pendulum swings forever because it's magic. No, it's not magic. It swings forever because we push it forever. We have a little boost mechanism at the ceiling. So the cable is clamped up here. And this little gold thing is actually a steel ball. And it's inside an electromagnet ring. And these little light gates turn on the electromagnet about halfway through the swing. And so it gives a little magnetic pull on the steel ball to add a little bit of energy, kind of like pushing a little kid on a swing. If you don't push them, you don't give them a little push, then they're going to stop swinging. Yeah, and this ring here actually has several other purposes. We can get into
How does
later.
that affect the direction of the pendulum?
What's that?
How come that doesn't affect the
So the whole goal is that this ball is uniform, the electromagnet's uniform, so that it should pull the same that way or that way or that way. It should be uniform. It should just pull it towards the electromagnet no matter which way it's swinging.
Okay.
Should. But what we have found is, first of all, at our latitude, how far north? 41 degrees north. It should take 37 hours for the pendulum to do a complete rotation. It actually takes 33 hours, so we're 9% fast. And we don't know exactly why. We have some ideas. Me and a fellow volunteer there have done some studies on this. And we found, so we call these racks, informally. These little sections, there's 49 pins in 1, 2, 3, 4, 5, 6, 7, 8 racks that go halfway around. And those are the little pins you hear go tink and they knock down every 2 or 3 minutes. So there are some of these that knock down faster than the others. These should be about 2.1 hours, but you'll notice this rack number 4, the pendulum flies through that. It's in 1.3 hours. And some of these others, 2.4 hours, 2.5 hours, 2.9 hours. So we think that boost mechanism is not neutral. We think it might be zipping it through this part of its rotation.
Does the time of year have anything to do with it, like close to the equinox or something like that?
No.
Okay.
Could it be that effect that we're talking about when you're on an angle, like we are, roughly 45 degrees or whatever, that at different parts of the rotation the effect is different?
I'm not sure I understand the question.
whether you're swinging up and down the spin that you get versus the amount of spin you get when you're swinging, whether you're swinging north to south or east to west. Is it possible that that the Focault effect varies?
No, because the Coriolis effect is independent of.
Okay.
It's like if you're doing artillery and you fire a shell, it turns clockwise in the northern hemisphere, no matter which direction you fire it.
Okay.
Is this specific to ours at this planetarium, this delay?
Actually, every pendulum that we have been able to get data on rotates a little faster than it should. Some of them dramatically faster, but most of them you can't really tell. But he found a paper in German that he translated some key pages from. Theirs rotates like 10% fast.
So we're
Ours is
working on
9% fast.
Koski theorem?
What's that?
You could name it after you.
Oh, yeah.
Koski has some.
This is a task-oriented question. Who sets up the little pins?
The employees, or I do.
Okay, so
If you see that they're down, you just go and set them up. Because it's way more fun when you see them get. Because otherwise, you can't tell. If you come in and swinging like this, and you leave it as swinging like this, you can't see that with your eyes unless you see. Oh my gosh! It knocked over 14 of those things.
You don't see the progression.
Yes, but you can see it very easily if you have the pins there to pins or pegs there to
So
make
if
it
the Earth
target.
was really flat.
Does the gravity of the moon have any effect?
It probably has some small effect.
Do all the pendulums use the same electromagnetic push?
So ours is driven at the top. Some pendulums have a steel core in the bob, and then they have a magnetic device on the bottom which drives it.
Okay.
And I don't, yeah.
Does that
So-
make any difference in the?
Not that I'm not
Okay.
super educated, but I know you can drive them from the top or from the bottom, and I'm not sure what's better.
Is there any variance day by day, or is it always constantly the same?
Well, so these are averages of about a week's worth of video. And it's not exactly the same, but there definitely is a strong trend. Like 4 is always fast, but it's not always exactly the same as it was at the time.
So effects like the moon could be significant enough.
Yeah, I don't know about that, but there is something going on. It's not super repeatable. And pendulums are known to be quite finicky. They're just almost impossible to set up and get exactly the theoretical value. It's just they're very picky.
If you turn off the boost mechanism, how long until friction slows it down?
Oh yeah, so that's fun because that actually happens. Every few months. It'll go from swinging out here and hitting them, and it will lose maybe 8 or 9 inches of travel in like 40 minutes, and not be quite hitting the pins anymore.
That fast.
And actually, whenever that happens, I pull out my stopwatch now because I want to see if the periods, because the periods should be unaffected. Remember, small swing has the same period as normal swing, and it is. It's up. The times I've been able to clock it is still 6.6 seconds to within the accuracy that I can measure. And I count like 20 swings and divide by 20.
I was just wondering if there were like any thoughts on how it's not really important, but just like any thoughts on how the electromagnet might like be tweaked a little bit.
Yes, the people, I'm a volunteer and we used to annoy some of the full-time employees. We want to go play with things and they're like, don't touch it, it's not broken. Leave us alone. So Dave and I, my PhD volunteer friend, we try and get them to do things and they resist us.
This is a psychology question. Maybe you have some insights. Why is it so hypnotic? I mean, why do I go there and sit there for hours and I can't pull myself away?
Yeah, I'm with you. I don't really know, but I'm right on board. I love it.
Have I suggested you guys try drugs?
Okay, so come visit the pendulum and we will talk. I mean, I just got started. I can talk about the pendulum for 2
Oh yeah, he can.
One more because it doesn't add any more information. If it knocked over a pin here and a pin back there, it's the same information as knocking over one pin. You don't need the back of the circle. It doesn't add any more information.
It's more fun.
this is a stupid thought, but could different pins have different resistance and that impacts different pendulums? Because it
Friction on
actually
the
takes a little bit
hinge of the
to
pin.
knock the pin.
Oh yeah, and there's lots of imperfections in the manufacturing of this. Some of them you have to hit them 4 times before they fall down. Others fall down the first time they get hit.
Seen that?
This plinth is actually not perfectly centered.
Yeah.
I mean, there's, yes, it's,
Could that explain the Koski hypothesis?
no. It's insufficient. Anyway.